Okay, good morning to all. Welcome back. So today I'm going to discuss about the semaphore. For the solution to the critical section problem, one synchronization tool is used, which is known as semaphore. Semaphore or S is an integer variable which is accessed through two standard operations such as wait and signal. These operations were originally termed P for wait and V for signals. That means P for wait means to test and V for increment. The classical definition of wait is wait S, and while S less than equal to 0, then there is no operation, that means test. Entry section code enter, critical section testing. Then the S minus minus, the classical definition of the signal S, and S plus plus. That means we can use semaphore to deal with the end process and critical section problem. The end process here is semaphore or mutex, stand for mutex means mutual exclusive. Initialized to 1, each process Py is organized. We can also use semaphore to solve various synchronization problems. For example, consider two concurrently running processes P1 with a statement S1 and P2 with a statement S2. Suppose that we require that S2 be executed only after S1 has completed. We can implement this scheme readily by letting P1, P2 share a common semaphore synchronization initialized to 0 and by inserting the statements. So S is a tool, or S is a semaphore, is an integer variable which is accessed through P for wait and V for the signal, and this is the definition of the semaphore, right? So next we're going to discuss about what are the classical problems of the semaphore. There are various types of problems which are proposed for synchronization schemes. So first one is your bounded buffer problem. This problem was commonly used to illustrate the power of synchronization primitives. In this scheme, we assume that the pool consists of n buffer and each capable of holding one item. The mutex or mutual exclusion semaphore provides mutual exclusion for access to the buffer pool and is initialized to the value 1. The empty and full semaphores count the number of empty and full buffer respectively. The semaphore empty is initialized to n and the semaphore full is initialized to 0. That means the semaphore assigned to n when the empty buffer and semaphore is equal to 0, and that means when the buffer is full. This problem is known as producer and consumer problem, and the code of the producer is producing full buffer, and the code of consumer is producing empty buffer. So the structure of producer process is as follows. What is the producer process? First produce an item in next P, wait for empty, wait for mutex, mutual exclusion, and next P is to the buffer, signal, then suppose the buffer is your empty, then signal is mutex, then signal is full, while 1. The structure of consumer process, this is the producer, and the consumer process is that do wait full for mutex, remove an item from buffer to next consumer, signal mutex, signal empty, consume the item in next, and while 1. So this is the producer and the consumer problem. Next one is your most important thing is your dining philosopher problem. What is dining philosopher problem? Is that is another method. Consider 5 philosophers to spend their lives in thinking and eating. Right? Very interesting concept. Consider 5 philosophers to spend their lives in thinking and eating. A philosopher shares common circular table surrounded by 5 chairs, each occupied by one philosopher. In the center of the table, there is a bowl of rice, and the table is laid with 6 chopsticks as shown in below. Okay. Consider the 5 philosophers to spend their lives in thinking and eating. A philosopher shares common circular table surrounded by 5 chairs each. And occupied by one philosopher. In the center of the table, there is a bowl of rice, and the table is laid with 6 chopsticks as shown below. So when a philosopher thinks, she does not interact with the colleagues. From time to time, a philosopher gets hungry and tries to pick up 2 chopsticks that are closest to her. A philosopher may pick up 1 chopstick or 2 chopsticks at a time, but they cannot pick up a chopstick that is already in hand of the neighbor. When a hungry philosopher has both her chopstick at the same time, she eats without releasing her chopstick. When she finishes eating, she puts down both of her chopsticks and starts thinking again. This problem is considered as classical synchronization problem, because here so there is the 1, 2, 3, 4, 5 philosopher, chopstick 1, 2, 3, 4, 5, right? When this philosopher starts to eat, he uses this chopstick and this chopstick, definitely. At the same time, suppose this philosopher wants to take the wants for eating, then what will happen? Because this chopstick is engaged by this, consumed by this philosopher. So this only option is that this one is the free, and it will use that thing and wait for this chopstick, right? Suppose this chopstick is also used for this philosopher, then what will happen? It definitely wait for the 2 chopsticks. So that is the dining philosopher problem. So this structure of the dining philosopher is to wait for chopstick, I plus 1% is 5, eat, signal chopstick 1, think. So that means this is also the mutual exclusion policy principle, because when that means the when one philosopher used the chopstick for eating, definitely other philosopher must wait till its other philosopher finishes the eating of the food. So that is the dining philosopher problem in the synchronization, right? So thank you for today's discussion, and this is the last one for chapter number 2. For next class, we are going to discuss about memory management of chapter number 3. Thank you to all.